In this video, we're going to work with this differential equation here. Y double prime plus y is equal to secant theta times tan theta using the method of variation of parameters. Now, our goal is to find our general solution y of theta, and our y of theta is equal to yc plus yp, and this has two components. Our yc is the complementary function and our yp is the particular solution. Now first let's find the yc, and to find yc, the complementary function, let's find first the auxiliary equation. And to find the auxiliary equation, we must refer to the left side expression of our differential equation y prime, y double prime I mean, plus y. And if you see y double prime, you just change that to lambda squared, and if you for y prime you just change that to lambda, and for y you just change that to 1. For example, we have here left side expression in our differential equation 2y double prime plus 3y prime plus 4y. Now our auxiliary equation here is 2 lambda squared plus 3 lambda plus 4 times 1 is equal to 0. That's our auxiliary equation in case this is our left side expression here. Now let's go back to our original auxiliary equation, lambda squared plus 1 is equal to 0. Now let's solve for our lambda. Our lambda squared is equal to -1, and let's take the square root of both sides. We have positive negative here, and cancel this. We were left with lambda is equal to positive negative square root of -1. And since our square root of -1 is just the imaginary number, now this is our lambda, positive negative I. Now let's change that to this format, alpha plus minus beta I. Since this is just equal to 0 plus minus I, we have this already written in this format. Now our alpha is 0 by inspection, and our beta is 1, the coefficient of the imaginary number. That's why we have it here. And let's substitute the values of alpha and beta in our complementary function equation here. Yc is equal to e to the alpha theta. Our alpha is 0, that's why e to the 0 is just 1, and we can neglect this. Our beta, on the other hand, is 1, that's why we have our complementary function as c1 cosine theta plus c2 sine theta. Now we already have our complementary function, and let's find our particular solution to complete our general solution. Now to solve for our particular solution, we have this format, y1 u1 plus y2 u2. Now our y1, we let this to be cosine theta, and our y2 be sine theta. Now let's solve for u sub 1 and u sub 2. Now, how are we going to solve for our u sub 1 and u sub 2? First, let's find the Wronskian w sub 1 and w sub 2. Our Wronskian is just a matrix consisting of our y1 and y2 in its first row and their derivatives in the second row. The derivative of y1 is y1 prime, and the derivative of y2 is y2 prime. That's our Wronskian. And our w sub 1, it's just the same format here, but we change the first column to 0 f theta, and our f theta also here is the secant tan theta, the right side expression of our differential equation here. That's our f of theta, and we just input that here in our second row, first column, for our w sub 1. Now, on the other hand, for our w sub 2, we change the second column instead of changing the first column to 0 and f theta. Now, to solve for u sub 1, we just integrate the w sub 1 over w with respect to theta, and our u sub 2 is equal to the integral of w sub 2 over w with respect to theta. Now, our goal is to find these u sub 1 and u sub 2, but we're going to use this w sub 1, and w sub 2 to find these. And after finding these u sub 1 and u sub 2, let's substitute that to our particular solution to find its value and expression. Our Wronskian is equal to, this is our cosine theta is our y1 and our y2 is sine theta, and the derivative is in the second row. Derivative of cosine theta is negative sine theta. Derivative of sine theta is cosine theta. And let's find the determinant of this matrix. Cosine theta times cosine theta is cosine squared theta minus negative sine squared, negative sine theta times sine theta, is this. That's why negative times negative is positive. We have cosine squared theta plus sine squared theta here is equal to 1. That's why our Wronskian is 1 now. Let's find our W sub 1. We change the first column to 0 and F theta. And let's get the determinant. 0 times cosine theta is just 0 minus second theta. Tan theta times sine theta is this. But we have to simplify this further. Sine theta, second theta is 1 over cosine theta. That's why we have it here. Tan theta is just sine theta over cosine theta. And negative sine theta times sine theta is negative sine squared theta. Cosine theta times cosine theta is cosine squared theta. Now remember this w sub 1. We're going to use that to find our u sub 1. Now let's find our w sub 2. We have cosine theta here, our y1, and the derivative y1 prime, negative sine theta. And changing the second column to 0 f theta, we have the determinant of cosine theta times secant theta times tan theta. And we'll neglect this because this is just 0. And simplifying, we have, since the secant theta is just the reciprocal of cosine theta, now we can cancel this out. Cosine theta over cosine theta is just 1. And we're left with sine theta over cosine theta for our value w sub 2. Now let's find our u sub 1 since we already found those values, w sub 1, w, and w sub 2. Our u sub 1 is the integral of w sub 1 over w. Since our w is 1, we can neglect this because our w is 1. And we're actually integrating w sub 1 here. In this case, negative sine squared theta over cosine squared theta. Now from Pythagorean theorem, our negative sine squared theta is just equal to cosine squared theta minus 1. That's why we have cosine squared theta minus 1 here. And all over cosine squared theta. Simplifying cosine squared theta over cosine squared theta is just 1 minus 1 over cosine squared theta is just secant squared theta. Now, when we integrate that, we can now find the value of u sub 1. This is equal to theta minus tan theta. And let's find also the value of our u sub 2. Integral of w sub 2 over w with respect to the theta. And our w sub 2 is sine theta over cosine theta here. This is our w sub 2. And let's integrate that, letting a is equal to cosine theta, and dA now is equal to negative sine theta d theta. That's why we have u sub 2 is equal to negative integral of dA over a. The integral of this is just negative of ln of a. And substituting back the value of a in terms of theta, cosine theta, we have negative ln cosine of theta. Now, we already found our u sub 1 and u sub 2. And let's substitute those values to our particular solution to find our general solution. Now, this is our y1, this is our y2, this is our u1, u2. And substituting those, we have cosine theta times theta minus tan theta plus sine theta times negative ln cosine of theta. Distributing theta, cosine theta minus tan theta times cosine theta is just this. Because this is tan theta here, sine theta over cosine theta. And we can cancel this. That's why we're left with negative sine theta here. And here, negative sine theta. And we're left with ln cosine of theta. This is now our particular solution. And now we found our particular solution and also our complementary function. Let's substitute that to our general equation. This is our yc complementary function. This is our yp, the particular solution. Let's substitute that to our general solution. This is yc and this is yp. But we can neglect this sine theta here because this is just, we have c2 sine theta in our complementary function, and we can neglect this negative sine theta because c2 minus 1 is just any constant. Any constant minus 1 is just some constant c2 also. So that's why the term containing sine theta in our particular solution, we can neglect that. That's why we're left with our general solution. Y of theta is equal to c1 cosine theta plus c2 sine theta plus theta cosine theta minus sine theta ln cosine theta. And we can prove that here that our answer is correct here. And that's all.